Hello. Hello, 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 hello. Good morning, everybody. A very good morning to you all. I'm Purushottam Ray, one of the organizers, and on behalf of the organizers, I welcome you to Fracmeet 2024. We have been organizing this conference for quite a few years now, in fact 12 years, barring 1 or 2 years during COVID time when we could not arrange this. So this conference is actually quite well known to the community, and this is the site where if you go there, you can get all the past, some details of the past conferences. So what happened is that during that time, 2009 and 2010, some of us, like Vikas Chakraborty and Alex Hansen, we thought that there's a growing community who are involved in this topics of mechanical properties or physics of complex systems. Because complex materials are becoming very important. People have discovered granular system, then sand piles, glass, and so on and so forth. It was there before, but it got a more kind of notice from the community, and because of that, the strength or the stability of these materials becoming very important. So we thought, and also we realized that not only over the Europe and Japan and United States, even in India, this community is growing very fast. Now we have a very big, sizable community in India. So we thought at least once a year if we meet, and also it has a lot of technological importance and also industrial importance also. So if we can have a meeting with engineers background and material science, chemistry, that will be very good. So that was the motive with which we started. And so from 2012 we started Fracmeet, and I have just, but you can visualize that even with this focus with the material stability, stability of complex materials, the horizon is very wide. You can talk about biological materials, as I told you, polymer, glass, so on and so forth, desiccation crack propagation, plasticity, dislocation motion, so friction, fluid flow through porous media, so on and so forth. And over the years, this Fracmeet, we have tried to keep this horizon in mind. And so these are the few Fracmeet banner I have put, that this is the 2012, the first one, fracture and flow in porous media. Then the next one is fracture from microscale process to macroscale responses. Then the other one, friction and fracture, bridging the scales. And then one conference we arranged in a nearby university, SRM. We were co-organizers, but it took place in SRM University, which is a couple of 100 kilometers north of the city, Chennai. So the title was Understanding Material Failure, 100 Years of Griffith Theory, because it was 2020. So as I mentioned that we missed 1 or 2 years during the COVID period of time, and 1 year the meeting was online. So as time flows, we come to the Fracmeet 2024, and the upscaling in complex systems, current perspective and future challenges. As I told you, so these are the organizers. My name is the last one, and Shubhadeep Roy and Deban Chakraborty, you will know them in due course of time. And again, on behalf of the organizers, hearty welcome to Fracmeet 2024. We are indeed extremely happy that people from all over around the world, from very far away countries, you have come. It is you people who have made this Fracmeet so pulsating, vibrating, and such a nice kind of meeting over the past. I'm sure even this time we will find the meeting extremely well. There's plenty of opportunity of discussions, networking, and this kind of thing. And I hope that you will have a pleasant stay in Chennai. Chennai is in south of India, in the coast of Bay of Bengal. So over the years, you will know the certain aspects of life in this place, and the food habit and way of life, and certainly, I mean, you will be able to get a glimpse of the city. And that's it. Thank you very much once again for coming. So, yeah. So we are now, we are going a little bit late, so we will start the technical session. And in this session, I will be the chair. And there's one speaker, Professor Vikas Chakrabarty from Kolkata, and he will be, Sakunjam, either finish it. Yeah. Yes. So Professor Vikas Chakrabarty, he will be talking on fracture story, a personal summary. Yeah.
So thank you for giving me this opportunity to share a personal view of a very short summary of some of the things. And I apologize for the audience, part of the audience, who had been in the SRM meeting last week, where also there was a fracture meeting, and I more or less presented the same thing. And yeah, so let me just tell you that, let me start now. Yeah, Robert Hooke actually first, this is part of our very first study or knowledge of physical systems. And it said that solids have a kind of springing, solids are springing systems, and it has a linear elastic response in the kind of thermodynamic limit it is defined. That was defined later on. Born and Huang showed that crystal structures and the knowledge of interatomic potentials are enough to find the elastic constants, and since the crystal structure is the lowest energy configuration of this many-body system, so the first derivative of the potential is 0, and so with strain, the next derivative will be quadratic, and that means linear elasticity will be from there, and this is a defined quantity for the solids, characteristic property of the solids, and basically coming from the interatomic potentials and the structure. In the textbook, famous textbook, Kittel, in the first person, he had 2 chapters on crystal structure and how to calculate the elastic constants, cohesive energy and elastic constants. And because Born and Huang was kind of developing the lattice dynamical things, so the first things were there actually. But then in the last chapter, and this is unfortunate, at least in the 53, first edition of the book, there was at least the last chapter which was talking of fracture properties of solids, which is essentially saying that, fracture strength is not really a direct property of the crystals or solid. It is probably because if you calculate from interatomic potentials and other things, you will get some value which you will never see. It will be much lower than that. And it is essentially disorder driven, a quantity probably not defined very well unless you give the details of the disorder. Unfortunately, this major property has not come to solid state textbooks, condensed matter textbooks, even today, although there have been a major development, and of course many of us are the real experts, and it is not there in the basic course of condensed matter physics in the systems, but it is probably one of the most complex. It has many complex of properties, and they are so common. We cannot avoid this property of solids or condensed matters. And it has been with us. I mean, a major observation was from Leonardo da Vinci, one of the greatest scientists world has produced, and of course he was artist as well as for architecture and all these things. He did a lot of research. He actually told in his notebooks that it seems there is no real value of fracture strength, any characteristic of the material. His particular experiment was that, I will have a little more details later, that if you take some iron wire from, and developed by the same process, and take different lengths and hang some load, if it is a smaller one, it will support some load, and then if you go take a bigger length of that and hang the same load, it will break. Then if you take, so it will become, the fracture strength will be lower. And if you make even longer and do it, so actually he observed that the strength of the solid decreases with the length, in this case length of the wire. And he kind of wrote that this probably is the reason why there are not very tall trees or big animals, because for the same strength they are very good and survive when, yes? Okay. So for the first thing was Griffith's nucleation theory, and yeah, there was a special meeting in 21 in SRM University, Fracmeet one edition there, and where this has been discussed in great detail. But essentially it is this, that suppose you have a specimen, say a slab of width W, which is like omega here, and it is under stress, sigma, small sigma, and it's an elastic one, and you have a micro crack of length 2L, I have just shown by a line, and which has to, under stress sigma, if it is going, if it is increasing on both sides by dl, so it has become 2L plus dl, 2 into L plus dl. Anyway, so if there is a micro crack or major defect in the system, if it is a linear elastic one, then the energy density, elastic energy density will be stress into strain. So it will be essentially stress square by the modulus of elasticity, and that will be affected. That would be essentially, if this crack were not there, it would be uniform, and but it will be kind of affected. This energy, because stress cannot be supported if you have the crack. And let me take a very simple geometry, that if there is a crack of length 2L, then this circular cross-section region with width W will lose its elastic energy. Now, if it grows by a further length, increase is by dl on both sides, then the elastic energy, additional elastic energy lost will be, this is the same density times this. Now, if you change, this exact geometry is not important here. If you change this geometry, the region for which the elastic energy is released, the elastic energy released region around the crack, the geometry doesn't matter, these numbers will change, but that will not, these numbers, only 2 pi and other things will change, but not really the physics. Let me tell you why. And this energy must be sufficient, at least more than these 4 cracks produced here, 2 surfaces here, 2 surfaces here. So that would be dl into the width of the slab times, so for the surfaces, and if surface energy density is this much, so this energy, released elastic energy must be sufficient to provide the surface energy required for nucleating the crack. So, and if it is more, then of course there will be sound energy that will come, and that of course happens. And so just equality will give you that this crack length, the crack nucleation stress will have the basic characteristic property of the solid, say linear modulus of elasticity, surface energy density, but most importantly it will be given by the crack length, the length inverse to the power half. Half is coming because if you are assuming linear thing, the sigma square will be the dimension of the energy that would be released, so sigma c would be given by 1 upon root L to the power half. And this has been a remarkable and very simple thing, and it has been tested in many by Anisul Rahman's group in Brookhaven in many with many potentials and in some details. I planned actually to show you an experiment, and this we would play with our with our mates, playmates or classmates, to challenge the friend to. So there are two deliberate cracks I have produced by a razor. This is the piece of solid, and the challenge is break this one without making a nucleation around this. So break that, and of course many of the playmates would say, I will give you my tiffin best items, say some sweets, if you can do that. So they knew, so others tried, couldn't do it. The reason is, this Griffith's law, if you have a bigger crack, that would actually, no matter how you do, this will break. And then of course if you put this. And then there are many other cracks here, they are not important. So this is, you can see that the extreme nature of the behavior is coming. Unlike linear elastic response and things like that, which depends, for example, these unbroken solids, elastic constant would be contributed by both the bigger defect and the smaller defect. So the statistics will be self-averaging. In the limit of volume of the system going to infinity, this elastic constant is defined. But breaking property, as Griffith showed already, is dependent on the extreme stress, because the biggest one, or here weakest one, will define the strength, not the others. They become unimportant as long as their stress release regions are not overlapping, as I did in the sample. Anyway, so let me go down to the next stage. Now this extension, this is precisely, this is precisely that to extend what Dogen was doing for, Dogen showed that even for disordered solids, extremely disordered solids near percolation threshold, the linear elastic constants like random resistor network, classical conductivity is also defined and self-averaging, not quantum conductivity as Anderson showed later. For the near percolation, conductivity will not be self-averaging. So, but anyway, for elasticity there is no problem, it is thermodynamically defined. So you get, it doesn't depend on the volume, you get a characteristic value of the disordered solid. Is it the same for this? Because Leonardo da Vinci was saying no, it is not, the volume is important. And this is precisely what was attempted by Purushottam and myself. The first one was in solid state communication, then Phil Duxbury and Leith. actually this showed how the Weibull distribution can come if you really use the percolation statistics. And Leith and others showed how the Gumbel distribution comes. And both cases show that, I mean, in the thermodynamic limit, the factor will go to 0. So again, sketch is like this, that if you have, say, instead of the previous one, that one crack, and I am now coming to a disordered sample where there are many, many micro cracks of different shapes and sizes, and typical elastic energy release regions, say, are not overlapping. So they are independent. Now, if that, then the failure probability of the sample, if that is capital F small sigma, so under stress sigma, can be derived this way. It is very simple. The survival probability is much easier because survival probability is 1 minus F sigma, and that is that all the cracks must survive. If small f sigma for the ith one is the ith say defect. So if each one survives, if any of them is 0, then the whole sample has broken. So if everyone survives, then only that thing will be the total f sigma. So that is actually the, well, if f sigma is considered to be small, then you can do a better calculation later. So is this. So the product over all these things are coming to the sum in the exponent, and that gives you the volume. Because volume, and then you say that the G is the density of cracks which are going to fail under stress sigma in the sample. Now this is something, we have the failure, failure probability of the entire sample given by exponential of minus b the volume of the sample times the density of cracks which are going to grow under stress sigma. Now, percolation statistics can give us the density of clusters, defects that will be produced, and how the length of the defect is going to give you the density. So that is, Griffith said how the length is connected to the strength of that defect. So let us utilize them in the next one. So GL, a near percolation threshold, goes as e to the minus L by xi. It decreases with the length and of the defect, but with a characteristic length which is correlation length exponent. A nu is there as p goes to pc. At critical point, you will have power loss. So the defects are not dependent on p because you are at pc, and then entirely it's a power law which is subsimilar distribution. So these are very well studied and all these things. So if you now use rather replace L by Griffith's law relation that sigma is 1 upon root L, assuming linear elasticity theory, then it is G goes as minus sigma square as p goes to pc, and G goes e to the power minus sigma to the power minus 2, and if at pc when it is power law, it would be like this. So f sigma would be either this form or this form. This is the Gumbel distribution form. This is by Paul Leith, and this and Purushottam and others showed that for the first time that if you assume a power law distribution, you actually get from percolation theory this cluster statistics, this thing, and that says that with volume, and f sigma finite means this has to be finite, and so either this or this, and in both cases there are different form of that. With volume it will be decreasing, the strength will be decreasing, and in last week actually Purushottam described in details that at fixed volume, not very large, but large enough, and P near P, see how the scaling behavior of the sigma C comes. And by the way, but if you, and that details I cannot discuss here again, and but there are huge literature how for a fixed volume, not infinity, and large, fixed but large, how sigma C goes as P minus Pc. These scaling relations, how to connect, I mean, one of them, the scaling relation with the fracture exponent, with the elastic exponent and things like that of these solids. So, and there has been a very nice experiment actually, okay, this is actually, okay. Benguigui did, from Technion, did a large number of very, very intelligent experimental kind of checking of them, and so that review is there. And in fact, that part is there only in this book, and so this is this. And this is what Da Vinci observed, that in both cases, if the volume increases, he actually tried a very simple experiment that this is taken from an engineering textbook. I didn't get the proper thing from the notebook, which I have an abridged version which doesn't give this picture, but it writes that, I mean, why big trees are not available, big animals are not surviving, and so on. And his idea was that, I mean, there is a bucket on which, and it is hanging by a wire, and there is a outlet of the sand which will be falling on this, and if there is a snapping of this wire, then this one falls, and there is a clip which stops the sand outflow, and then by measuring the load at which it has broken, he would get the breaking threshold, and he found that it decreases with volume. He didn't mention about these kind of precise forms, but anyway, these are now engineers have done it, and these are now very well settled literature. Then comes fiber bundle model. This is a fantastic and very elegant model. It was first proposed by a textile engineer, Thomas Pierce, and this journal of Textile Institute is no longer surviving. Remember, this is actually 1924, 25 is the Ising models publication. Thesis submission was 25 perhaps. Ising was doing it for cooperative interacting systems, and this is cooperative dynamics, a very simple model. And this is actually the Ising model of dynamical failure, and that was by Pierce in 1926. A particular solution for the for the strength of this system was published by Daniels in this. Then I think a major, I mean, how the avalanches of failures occur in such bundles, and the precise power law near the failure point was first proposed by Professor Alex Hansen and Professor Hamer, and this is a classic paper. And after that, one simple paper which actually tried a very simple thing, that you take a kind of which allowed some exact calculation and show that critical failure strength in this model, in some limit of equal load sharing model, this I will define soon, has a fixed value. This is not dependent on the volume, that means the number of fibers, it is not dependent on fibers. If you consider that all the fibers are hanging from a rigid rooftop, rigid and under the stress kind of things that will be required here, and also the lower platform from which the load W is hanging is also rigid. If they are rigid, that means there is no local deformation. I mean, the thing is, if one fiber fails, there is no local deformation. If there is no local deformation, then the entire load is shared equally by all the other fibers. This is the mean field theory, I mean, we do in statistical physics. There is no fluctuation in this load sharing, and which would be different if the equal load sharing version, which we are considering now, would not be there. But if it is so, then it is fantastic. Then if you assume that the fiber strengths are uniformly distributed from 0 to 1, I mean, highest strength of the fiber is taken as, say, I mean, normalized to 1, and the probability of getting any fiber is uniform. That means from 0 to 0.1, the number of fibers in this bundle was the same before it broke as, say, 0.9 to 0.9 plus to 1, or anything in between. So it is uniform. If so, then you know, if you know at any time what is the, because you know that when they were all there, the load was being shared by all, but if some of them are failed, then the others are, so at time t of the failure process, the sigma per load, the load per fiber, surviving fiber, would be greater than what was original. Now, if any load per fiber is there, then up to that much will be will fail, and surviving fraction will be 1 minus sigma t. Now, how to calculate sigma t? That is very simple, and that would give us many things, and those things are actually reviewed very well with Alex Shutoshi. Actually, Shutoshi did many of these things, who is unfortunately not here. Then they have a nice book, very nice book, and giving also some of the history of these developments. Unfortunately, these are not part of our condensed matter courses yet anywhere. And anyway, so okay, the idea is that each fiber has a linear elasticity, and the slope is the same. So that means if there is a failure, the entire slab goes horizontally down, so that's the only thing. And if even the failure stress, I mean, this is stress and this is strain on the x-axis, so if failure stress would be also the same for everybody, every fiber, then of course it would be an interesting system. But what Pierre said, that if they are have a distribution, and that distribution, if it is so, we are considering now. And another important thing is that we have assumed the platform to be rigid enough under this kind of load scenario. Then if the fraction of fibers, intact fibers at time t is denoted by ut, then ut would be 1 to start with, as you have put some load. Then these dynamics, which you can easily find out. As I said, u of t plus 1, if you discretize time t, will be 1 minus sigma t, because what is the load now? The revised load per, or redistributed load per fiber, that is sigma t. But that means the entire load w by n into ut. So that means ut is 1. This is the simple nonlinear equation, and you can have a fixed point or you may not, and you have a runaway situation, and if the load is less than the critical threshold, which in this simple form is 1/4, if you normalize the highest fiber strength as 1, and then you will have a kind of ut behavior like this. It stabilizes to some value beyond half, but goes as sigma c minus sigma to the power half. Then you can define load susceptibility. I mean, you increase the load a little bit and then take the derivative, and that will go as this. You can see that these are not exactly the Ising exponents in the mean field limit. So there is a different scaling relation. This was derived nicely by Shoumo and others for this limit. Manna was also involved in this. And anyway, you can also define how the dynamics will grow near the critical point, and that goes the dynamic exponent and so on. And you can find these scaling relations. Interesting thing is, in this equal load sharing limit or ELS limit, you have a precise critical point which will disappear and become volume dependent when you allow this local deformation, and the load sharing will not be equal. So this is the story. But this gives one more important thing. How much time do I have now? Because I have now come to the real thing. I want 20 minutes, okay, I have. Remember, now we have in this model, and this generally shows that failure threshold is actually a critical point of a cooperatively, the dynamics is cooperative. If one fails, the others try to share that extra load. If they cannot survive, they will fail, and then finally it stops, and the sample still remains hanging. The load is still hanging from the system fibers. If the extra load can be shared, and if not, depending on the load distribution, fiber strength distribution in the system, it may not, or it would be. So there is a critical point, that is sigma c. Around that point, every power exponents in this model, mean field exponents, will be there, and it's precisely following the scaling relations. This is different from the Ising in the mean field limit, but there are fantastic interpretation in terms of, Kolmogorov distribution of avalanches, or turbulence, and that was done by Shomo and myself. And now I come to one of the perhaps most interesting thing, and this critical point in physics has been taken to, because critical point in physics is not universal. Even in Ising magnets, it depends on what is the strength, nearest neighbor strength, and so on. Only the, in physics we actually, or statistical physics, we look at the biggest or the order parameter, and which is often related to the biggest cluster, avalanche, or so on, and here also. So just looking at the, you can, if you have a model, you can find the critical point, and exponent is universal. So that means if you do not change something, the exponents will not change. That much is assured by this. Some very subtle features are needed to be changed either in the interaction range or in the dimensionality of the samples, or sometimes some other points, very subtle features, on which the exponents, the critical behavior near the critical point. But critical point is not known. There is no method to find the critical point. Of course, if people do not, it doesn't matter. If you are taking a ferromagnet, if it has a different temperature, you can go from below transition temperature to above transition temperature, come back and see what is the critical point. It doesn't matter that, because the system survives. But often, the breaking is below critical point, you are alive, and after critical point, you are not alive. So it is a life and death problem, and that is also a critical point that can be shown in many of these models very clearly. The problem is we do not have any experimental way of measuring. All these statistical physics methods that we do fail, but there are reasons the self-similarity occurs only near the critical point where we can actually calculate all these things. This is the renormation group story and so on. But there were another group of statisticians who were doing statistics for so many years, particularly for social systems. What we are doing since our Maxwell-Boltzmann distribution thing, energy is not uniformly distributed among the basic constituents, say atoms, molecules, or basic ingredients. When they are in equilibrium, Gibbs distribution and so on. Basically Gibbs distribution, and depending on the momentum energy momentum relation, you can get that. If you look at in 50s, for 1905 actually, Max Lorentz, this is not Frederick Lorentz of physics, he actually suggested that maybe the economic inequality, they are also thinking of economic inequality, they are not that much interested in the real distribution. Most important is how to measure the inequality. And they do not really go for the richest person or in the society, because that doesn't give much things. Of course, that has to be found out. But there may be several richer, I mean, I will come to a very common thing that you know. And what Lorentz specifically suggested, you arrange the society, the people, from poorest to the richest. Fraction of people on the x-axis and arrange them or order them with the lowest wealth to highest wealth. Okay? And on the x-axis, y-axis, this is on the x-axis, and the y-axis, you collect the cumulative wealth of those people. So 0.2 fraction of people would have 0.2 fraction of wealth. 0.4 fraction would go 0.4, 0.8 fraction would go to 0.8 if everybody was equal. But since they are poorest to richest, of course it would go to 1. It has to be, because the total thing. But poorer people will not have that much wealth, and gradually the people will go to, finally it will be, and that would include the rich people as well, of course. Richest one, of course. But this is the entire Lorentz curve. So instead of distribution, this is called the Lorentz curve. Any textbook in mathematical statistics will be actually giving that. And the equality line, any economic student will only know this thing. And Gini, Corrado Gini in 1914, gave the Gini coefficient, which is now in newspaper also gives the Gini coefficient sometimes. What is Gini coefficient? I mean, it's very simple, how to measure the inequality in the society, not just for the biggest one. I will come to the biggest cases very soon, and which didn't really take proper footing until we brought it back. But anyway, the general inequality is measured by this area, and if you normalize, I mean, because the highest value can be half, so normalize by this area. So this area divided by this area is twice of this area, and so on. That's the Gini coefficient. You will see that Sweden or some such European countries have about 0.3 Gini, whereas for India it is said to be about 0.41 now, but it is decreased. I mean, it has certainly decreased, it looks like. But some people say, no, huge inequalities have grown and so on. But somehow it's true, this Gini coefficient is only one thing, which is an average one, and that doesn't really give everything. There was one observation by a famous engineer, but he is best known as best social scientist, a very eminent social scientist, and this is Pareto, Vilfredo Pareto. He actually said that in Europe he observed that typically 20% of the people possess 80% of the wealth. And he had exact statistics from Italy, but his idea is that many other measure is showing that. So this is called 2080 people, 2080 kind of inequality, or 80-20 inequality, and except in management, where they actually plan for some major investment using that law, it's not a part of economics. But one simple quantity is that another, draw the perpendicular diagonal and find where this Lorentz curve is cutting it. Now you can see that, by construction, if this is 1 minus k, this is a 45-degree line and this is a square. So this is also 1 minus k, this is 1 minus k, this is 1 minus k. So that means since this is totally 1, this has to be k. So 1 minus k fraction of people are having k fraction of wealth. If k is 0.8, here it is not, it is below point, what I am showing is this. If k is 0.8, Pareto would be right. I mean, Pareto was just giving one example what he had observed. Now, since then, we actually tried to check, because economic data are, there are many ways of manipulating, but then you can have a simple thing. I mean, I think Oshim did this thing, Oshim Ghosh. He just tried to find our citation index. Just go for Web of Science, take some individuals, very high, prolific and very successful researchers, or take some of the best universities and also some not so well-known universities, not so established universities. You can see that the number of papers that are published, say from Harvard for the last 10 years, and how many citations, all the papers have not got similar, equal citations. So I have say 10,000 papers from 10 years, and it's much more than that, but let us, some from say Oxford or Harvard. And then I have the community wealth is their total citation that day. So how many papers have got, I mean similarly, even from Harvard or from Princeton or Cambridge or even say Math Science will have the same structure. This is the Lorentz curve, find the Lorentz curve for this. And these are easily available, and you can easily find how remarkably correct Pareto was. The K index is about 0.78 to 0.86. This was published by Ghosh et al. By us in 14. I mean, so it looks like the better the university, the better are the things, but it doesn't really go very much beyond Pareto value. It doesn't go that one person from an university is doing everything and all the credit is going to him. Typically, 14 to, 20% people or papers are within them. The average income is changing. That is everywhere. I mean, that all the Gini coefficients of the same Gini coefficient places do not have the same average. The distribution is unequal. The distribution inequality is never going beyond 0.8 limit, something like what Pareto said. It is actually around 0.86. And then let me finish very quickly. We did a remarkable test that these social systems are like self-organized systems. This has come, I mean, unless you are tampering too much by major military force or some forced socialism and things like that, you will have this thing. And if they are social, if there is no kind of social support to those who are failing, remember, most of the best universities, best education centers do not encourage any, they encourage competition. And if you are not, if you are failing, you have to get out of this system. Now, this we cannot do in the society. That's fine. But if we would do, would it be that only one student or one faculty or one professor would take away everything? No. Nowhere it is happening. Equality is happening to very, very poor universities, poor standard universities. So equality is not really encouraged. But it comes to a very high inequality level, that's 0.86. And you can see, I think, Jordi Barrow will have also some experimental result. There is one experimental result, and we have shown some of the not ELS model, where we do not have any theoretical calculation, where this will be shown that it is actually going to 0.86 before breaking. So the K index, the Kolkata index, and Gini becomes around 0.86. Gini also becomes very high and it becomes same. And that is a major way of predicting where the failure will occur, because so far we didn't have anything. And now let me give you a, oh sorry, yeah. This is a theoretical calculation for the equal load sharing model. Equal load sharing model is not self-organizing one, but it has the benefit that we have given the calculations earlier, and this is the remaining fraction fibers, that the fraction of fibers remaining at time, at under stress sigma, the fixed point value of that, and du d sigma goes as this. If you define that as an avalanche cluster size, then the Lorentz function that I discussed in my earlier mail, the Lorentz function can be, you can get an exact form for that, and this will be this, and so Gini coefficient is exactly calculable 0.33, which Sweden and others say, and Kolkata index or generalized Pareto index will be exactly root over 5 minus 1 by 2 is 0.62. Now, this is something, an ELS model, fiber bundle model, but with various kinds of distribution. You know that the calculation I showed, or this thing originally, was using fiber strength distribution uniform, which is very simple, and then you can do the exact calculation very easily. But here, if you can take many other distributions, but assuming that this platform is very rigid, and this platform is also, this roof is also very rigid, but the distribution may have various forms. Now, if you do that with very popular evening exponents of Weibull modulus and various system sizes, and increase the load with time, and after failure, the system, this is the Kolkata index, and you can see that after some time, this is the time versus Kolkata index versus time. You can see that it comes to about a little bit above 0.6, but for different system sizes, they are actually in different places. So if time is scaled by the system size properly, then they are in different places. So essentially around 0.6 to the system phase. So if you're, go back to, Lorentz curve. For avalanches, you do the same thing from biggest to this, and as the system size is, the load is increasing, the various avalanches are coming, you draw a Lorentz curve at every time, and if the Kolkata index, which is this coordinate, is coming to something like is below 0.6 or so, you are still safe. But if it crosses that, stop it, because very soon the system will fail. So this is, and there are many other very good papers. Yeah, thank you. I have finished. So there are kind of very good papers. And also, how the standard things are done. Somaditya and Soumyajyoti, they actually, through Gini index, they actually showed how the scaling standardizing model, or even some fiber bundle model and other things can be analyzed and get all the results that you need and that you had been obtained. You get some extra thing as well. And because, as I said, for self-organizing system, and then self-organizing, then there is this thing also with Diksha is also here, and Sumati is not here. So anyway, and there are other things they have now, Shomo and his collaborators have published, I think last week or week before the last one. they have also another big one. And they are saying that these things, Kolkata index and Gini index, are very good helping how to look at the critical point and also give the old physics model things very nicely. I think that one also is published now. That is also another physical review recently. Okay, so yeah, this is what I wanted, and I think we have long neglected another statistics group who were studying inequalities. We have gone to the inequality and always looked at, in physics, always looked at the critical point and then self-similar one and all these things. So in a sense, we looked at the richest person in the society and could not really get anything what is happening elsewhere. Statisticians, social statisticians, were actually trying to take everybody into account and then trying to see how the inequality is growing. And yeah, and they could they actually observed, I mean, that there is something, but they didn't, I mean, actually Pareto said when range was, didn't even put forward. I mean, Pareto said it before 1900, something like 2-3 years before, and that 80-20 law. So there was, and nobody actually took it seriously and then didn't do it until we thought that maybe this is what is happening, looking at the citation statistics of most of the very good people and very good universities, that they are extremely unequal, and even within their publication. Incidentally, Google Scholar has a site for Karl Marx. Karl Marx is one of the highest cited person even today, and that site is maintained by British National Library. So you can depend on that data. You just analyze that Gini coefficient is about 0.86. Remember, his own publications mostly books, letters, and these are highly cited still today. And huge number of citations, huge number of writings, and they have, and K index is 0.88. So he has gone past K equal to G, and which is actually, he is in the self-organized critical limit, which is another Manna and Shomu and myself have published already some time back. I mean, that in self-organized critical model like BTW model or Manna model, these things were checked, and we found that yes, these models, before the self-organized critical comes, the Gini coefficient Kolkata index becomes same and they cross, because Gini starts from 0, Kolkata index starts from 0.5. But finally they cross, and then in self-organized systems, they actually remain there. This is shown for the physics models by one of the originator of this self-organized critical model. He was one of our colleagues earlier. So Manna and one of our all colleagues, and together with him in his model also we found that it is actually true. And then there are many things, and this paper in PRL last year, they showed all the physics things can be obtained from these things. Beautiful scaling behavior and everything can be reproduced. Additionally, you get something which you cannot get from statistical physics that we do today. Anyway, thank you. I think this will be a very important development very soon.
Thank the speaker for the wonderful talk. So,
Yes.
there's time for one or two questions, quick questions if you have.
Yes,
Thanks for the talk. So when you showed these results by the Firebanda model with the Gini and Kolkata index, it looks like the indexes, the Kolkata index go back a little bit at the end of the...
yeah, that happens because what happens is before the final failure, some samples have failed earlier, some samples failed here. So these Gini is slightly, because some have already crossed 0.62, some are not yet. So something like that happens because the samples are not surviving near before, because the real threshold should be say 0.62. But if you run 100 thing, maybe 50 are actually failing before that. And that kind of thing, 10 are actually there. And then eventually if you go beyond, then of course everybody will fail. So yeah, so those things are there. Maybe Shaumu can tell better about this thing, but I think this is the main reason. Yeah, you are right. I don't know what happened. Oh, already I am dropped. Okay, thank you. So yes, you are right. What is that? Sorry. Yeah, I should have pointed this way. Yeah, so you are right that, but essentially around 0.62 this is happening. I mean, maybe you have to be, I don't know, up to 8,000 systems, sorry, what was the system size? 20,000, up to N 20,000. Still there are, I mean, some systems are failing. I mean, some of the samples are failing before 0.62, some are later. And some things are actually responsible for these fluctuations there. So it's essentially around 0.6 you are safe, but if you are going there. But it, as I said, if you have a realistic sample, like where stresses are redistributed with nearest neighbor fibers among them, then of course it will go to higher values. And in some of these self-organized, self-organized, not critical but dynamical models, it actually goes to 0.86 or something. And these things are published actually in some of these publications you can see, and some more publications from his group have already these things.
Any other question? If not, then let's thank the speaker once again. Anyway, we can discuss.
Yeah.
So there will
sure.
be now tea break for, well, half an hour. We will come back at 11 o'clock. Tea and coffee is just outside. And you can collect your user ID and password from the